Okay, so we talked about an overview of multi-scale modeling. Now, these multi-scale modeling will be applied at different materials classes. And based on the class of material, we want to use different simulation or modeling methods. So it's important to learn about materials classification and basics of material science. So we learn about what are materials, what are the classes of materials such as metals, ceramics, polymers, and composites, and what make them special or distinguished from each other. So let's talk about material science basics first. A material we can define as a substance or mixture of substance that forms an object. We are surrounded by different types of materials. So it can be pure materials or it can be impure materials with defects. It can be living material or it can be non-living material as well. So the fundamental principle in material science is very interesting. So it depends on the processing, structure, property, and performance. So when we say processing, it can be, for example, heat treatment, or it can be, for example, how we solution processed a material, and so on. So based on this processing, it can have effect on the structures. That is how, based on the processing, how does it impact the structure in terms of atomic structure, nanostructure, or macrostructure. So based on the structure, we can have different property. So an example on the left-hand side, I show you how, based on the heat treatment, a materials is processed. And on the right side, I show you a structure of a diamond crystal structure. So based on the processing and structure, we can have different properties. So these are measurable material behavior, including mechanical, electrical, and thermal properties such as strength, ductility, elasticity of steel. And based on these properties, you might have different performance. That is how a material will behave under real world applications. An example would be tensile test for predicting the steel's performance under the load. So these are very specific examples for mechanical engineering applications and very important to learn before we apply a modeling technique. So as we mentioned, there could be different classes of materials such as metals, aluminum, copper, so on, or there can be ceramics, which are more brittle than metals, such as silica, glass, alumina, quartz, or there could be polymers, such as the polybags we use, or polythene bags, or Teflon, or Kevlar, and so on, or there can be composites of these three, such as wood, concrete, and so on. So what makes them special and make them distinguished from each other is different bonding environment. So there are different types of bondings, such as ionic bonding, where we have an idealized ionic bonding of oppositely charged ions, such as sodium chloride, or there could be covalent bonding, such as the sharing of electrons in carbon, so that we have covalent bonding. Or we can have metallic bonding such as copper or aluminum, where we have a cloud of positively charged ions immersed in a cloud of valence electrons. Or there could be van der Waals bonding, where we have neutral molecules held together by a weak electric force known as a van der Waals bond. So based on these electronic cloud, we might have different classes of material, and that's why it's important to know electronic structure of a material. We will talk about during the density functional theory module of this course. And based on that module, we can determine the properties such as the elastic constants or bulk modulus, and based on that, that will feed back to the multi-scale modeling of phase field, or it can feed back to the finite element simulation and so on. So it's very important to understand different bonding environment that we are dealing with. So just to recap, metals have metallic bondings, have delocalized electrons, or that forms a sea or cloud of positive charged ions, or it can have effect on conductivity, malleability, ductility, and so on. Similarly, ceramics have ionic or covalent bonding. So these have special features where for ionic bonding, we have electron transfer between metals and non-metals forming charged ions, or for covalent bondings, we have electron sharing between non-metals leading to directional or strong bonds. So these leads to the hardness and brittleness, which are characteristics of ceramics, or high melting point and chemical stability. Similar to polymers, they are usually covalent bonded materials. So these have long chains of molecules connected by strong covalent bonding. And that leads to properties such as elasticity, plasticity, tensile strength, and chemical resistance. Similarly, for composites, we can have varied bonding because they are combinations of metals, ceramics, and polymers, and this leads to enhanced mechanical properties or tailored functionalities, improved durability. So that is the importance of mixing different classes of materials in composites. So as we talked about, there could be perfect or defect materials. So these defects could be of different types. So it could be vacancies of atoms. So for example, on your right hand side, I show you how we have an arrangement of atoms or spherical blue balls here, and there's one atom missing. So that's a vacancy defects. Or it could be interstitial defects where there could be an arrangement of atoms, and they're in the intermediate zones, there are atoms lying there. It can be substitutional atoms. These are the classes called point defects. Or there could be line defects, where instead of having one atom missing or one atom misplaced, we will have a line of atoms which are missing or misplaced. Similarly, there could be surfaces where instead of having a single atom missing or a line of atom missing, we'll have a block or surface of atoms kind of missing or misplaced. Or there could be grain boundaries. These are called area-wise defects. So we learned about in this module different types of materials, what leads to different types of materials, and there could be both perfect and defect materials, which are very important before we go to the modeling of these materials.